Hello and welcome to our webinar, Continuous Integration for Embedded Systems. I'm Thomas and I'm going to share a little information about this and do a demonstration about how this can be done. Okay, let's get started. Why do we want this? Why do we want continuous integration? Basically, the topic is we want to test early and we want to fail earlier because we need to fail as fast as possible to fix the bug as cheap as possible, as fast as possible, because it gets more and more expensive the later we get in the process. So for example, a system test usually is very expensive already, or even an integration test. After the release, it gets even more expensive if you have to call back equipment and so on. But even a system test might take days or even weeks to run, and the effort is usually very huge. So the goal here would be to bring the integration test and the system test to the desktop of the developer. So while he's developing, the developer wants a fast feedback. Let's have a look at the development process and how testing plays into the development process. So if you look at the typical development process for an embedded system, usually you start at an evaluation board, just as an example, and you configure your drivers, you test your drivers, you try them out, and then you develop hardware-related software components, for example, a motor control, or a battery control, bus-related or low-level bus-related protocols like CAN, LIN, and so on. And in the end, you place your software components, your application logic. On top of that, you integrate this into an application. And in the end, you go to the real hardware, to the real electronic control unit. And the normal places where most projects test their applications are here. So in the early phases, usually only unit tests are run because they can be run only as software tests. They are cheap, relatively cheap. They are good to automate. So you can start there, of course, and that's a good idea, but it's not sufficient because it's really hard to test the drivers, to test the hardware-related software components. For example, a motor control, that's really hard to test with a unit test. So later in the process, you can run a hill test, hardware in the loop test, big one for your complete system, or a real system test. So you get into the car and drive around the block. But that's already very expensive and usually is not run very often because it's so expensive and the equipment usually is not available for automation because it's so expensive. So what we do is we focus on the hardware-software integration test for the early stages of the development, or basically for the complete development cycle, but with an emphasis on the development of the software. And we test, for example, on an evaluation board, the complete software stack. And this allows us to integrate this with continuous integration, because we do not need the real hardware in the system. So what do we really want and need? We want to test, and that's the most important thing here, we want to test what is changed most frequently, and that's your software. Because the hardware usually is changed every couple of weeks, later every couple of months, but the software might be changed 10 times, 100 times a day, depending on the size of your project. So I think that's the most important thing you want to test most frequently. So what you also would like to have is to test every code change of every developer within minutes instead of weeks, because every code change can have malicious effects on your system. And if you know it within minutes, you can fix it immediately because you still know what you did. After a month or so, you have no idea what you did. And after a month, there might be another 500 commits by other developers in the system. So it's really hard to nail down the problem. Another thing you need is a full regression test, because even in normal software systems, it can happen that you change something over there, and over here you have a bug. And that's very frequently the case in embedded systems, because you have the same memory space, you have very reduced resources and so on. So you need to run a full regression test to really make sure you did not break something else, even if you tried it out, what you changed, but you need to run a full regression test. And another thing you might want to have is a full test automation to enforce tests and save time through automation, and that's where continuous integration comes into play. Continuous integration helps you to completely automate your test, not only to push the button and let the test run automatically, but to run it on every commit. Another thing you need for an embedded system usually is an automated hardware in the loop test to test more than pure software units. Software unit test is good, but it's not enough to test your complete software stack. So why do we want continuous integration? Let's have a closer look at that. Let's have a look at the integration problem. We have the integrator. This can be a person, this can be a team, this can be a role. And the integrator is responsible to integrate all the changes of all the developers and make sure that they build, that the quality is high and so on. So he integrates all the deliveries into a product, basically. So the first developer has 20 changes, commits them, integrator is happy, not much to do, 50 more changes, 30 changes. So, and then suddenly a lot of changes come in, and the integrator gets a little bit yellow, and more changes come in. And in the end, the integrator thinks that's integration hell. And that's exactly this situation when everybody throws his changes in maybe 5 minutes before the release, maybe 2 days after the release. We've been there all. So that's a really, really bad situation, because the conflicts you can potentially get, or the problems, they multiply. So it's not 20 plus 30 plus 30 changes, it's 20 by 30 changes, by 30 changes, by 500 changes, because they multiply, the problem multiplies here. And if it happens 2 minutes before the release, that's a real problem. So that's what we want to avoid. So how does continuous integration work? Imagine you have all your developers here, they all commit to the source code repository, source code management system, for example, Git. And every commit triggers the continuous integration server. In this case, for example, a Jenkins server, could be a GitLab, GitHub server, and so on and so on. And the server checks out the latest version of the commit, the latest commit, automates the builds, automates the test, and potentially automates the releases. Please do that. That's a very good best practice. To automate the releases saves a lot of time, and that's also basically a test, because then you know that you can release anytime. So please automate this as well. But we're focusing on the test now. So the idea is every change is integrated and tested. Every change, not nightly, not weekly, every commit. Then another thing is commit early, commit often, fail fast. Because if you commit early and often, you give the continuous integration server to fail fast, to run the tests fast. And after, if you commit every month or so, then you lose the opportunity to fix your bug really fast. So fail fast is important here. Then by doing that, the bugs can be detected and fixed very early, sometimes within minutes. That's very important here. So what are the rules and principles of continuous integration? One thing is quality equals speed. and it works in both directions. Speed equals quality. That means if you are fast, you have time for quality. If you have high quality, you speed up your development process. So those two things belong to each other. Then commit early, commit often, because you want to fail fast. Then never commit broken code. If you commit broken code and the compiler can't even build the system, you invalidate the continuous integration for everybody else because it cannot build. If, let's say, if you have 100 tests and 5 tests fail, that's okay. You need to fix this as well, but still the other tests work. So if somebody else commits something, he can still use the continuous integration. If you commit broken code, it doesn't work anymore. So the other way around, fix build problems immediately. That's very important to avoid this situation. Then fail fast. For fast feedback means if you have long running tests, make staging. So staging means in the commit stage, so whenever somebody commits, run your fast running tests, build the system, run your smoke tests, run your whatever is running fast within minutes or half an hour or an hour or so to get really fast feedback. And if you have long running tests like robustness tests, stress tests, and so on, run them overnight, run them over the weekend, automatically, of course, but test every commit. That's very important. Then act on metrics. That means whatever metrics you have at hand that are useful to trigger search for certain problems, or to avoid certain problems. For example, if you're running into memory problems, yeah, why not creating a metric? Your compiler does this anyway, that tells you the high watermark of the memory you will consume in your application. And if you hit 70%, make a warning. If you hit 90%, make an error. And so that way you know early in the process that you will run into a problem in the next week or so. Then build for all targets. If you have several different targets, build for all of them, because if you build and run a test on one target, you still might have problems on another target, and you can at least compile it for the other targets as well, because a compiler run is also a test. It's a static code analysis in essence that tells you, first of all, that syntactically your program is right, and also the compilers have a lot of warnings that might give you a hint of potential problems. Then release and deliver always, because if you release and deliver always, you know you can release and deliver always. You don't have to send this to the customer, but build the documentation as well, build whatever is needed for a release. And maybe you might want to release this to the system test department or to the beta users or whomsoever, maybe to the colleague sitting right next to you. That helps a lot to speed up the process. So test automation is a precondition for continuous integration if you really want to use it. So if you do not have any tests, it's valuable, but it's not as valuable as it could be. Let's have a look at the different levels and the different focus areas of focus of tests and test methods. Let's have a look at a typical embedded project. You have an electronic control unit, including the microcontroller with the software and the drivers. Then you have some power electronic sensors, actuators, and so on your ECU. And then outside your ECU, we have the real system, for example, a motor, a pump, a hydraulic system, whatever it is. In this case, could be a lubrication pump or something like this. So you can start with the unit test. The unit test is the smallest possible test probably in an embedded system. So you test one unit, that means one C module or one class on that level, so on class level. You can use a unit test tool, unit test framework to do this. It's a pure software test. Then You can run a software integration test. You bind together several units, make still a unit test. So it's a unit test framework you can use for software integration tests. Some units you might not be able to test with a pure unit test because, for example, a motor controller with a loopback control, with a closed loop controller, that's really hard to test with a unit test because you need an environment simulation, unit history, and so on and so on. So, but usually you can test a lot with unit tests, but it's always pure software tests usually. The next level would be the first level of hardware in the loop. That's basically the smallest possible hardware in the loop test. We call this a hardware software integration test. That means you take the microcontroller with the complete software stack you're deploying to your customer, and you test the microcontroller, including the software, as a black box. That's relatively simple to do in comparison to a system test. So that's where we designed the mini-hill test environment. And the next step would be, let's say, the big hardware in the loop test, very useful, but already very expensive and usually a lot of effort involved because you need to simulate, for example, really the moment of a motor, or you have maybe 24 volt signals or 400 volt power electronics and so on. So that's where it gets really expensive and slow. And the last step would be a system test. So you get into the car and drive around the block. That's, of course, the most expensive test usually you can do. So the effort and the cost, they are really low at the unit test and are really high at the system test. And so unit tests and software integration and also the mini-hill here, they are really easy to automate with continuous integration. And the further down you get, the harder is it to automate. For example, a system test to get into the car and drive around the block, that's really hard to automate or not to automate. Let's have a look at the typical continuous integration delivery pipeline. So you want to make a commit, and what do you want to test in a commit? So let's start with a regular software project. You're in a commit stage, you want to build your software, you want to run maybe static code analysis, metrics, unit tests, maybe a software integration test. So maybe on a unit test level, basically on a pure software test level. Then the next stage would be a hardware software integration test, an acceptance test. So this could be the acceptance test stage to make sure that your system, for example, your software system plus your microcontroller, they work together very good. Then the next step would be a capacity test stage, something like performance, robustness, safety tests, and so on. Some of them take very long. That's why we use staging to run them. And the next stage could be a user acceptance or system acceptance test stage, where we run a user acceptance test. Hard to automate. So user acceptance, maybe you need a person to really verify or validate that the system does what it's supposed to do, or a software system test. That's the level where we for the user acceptance test stage. And in the end, you make delivery. In the field of embedded, you have maybe different tests. For example, a software in the loop, model in the loop. That's usually very, very fast. So you might be able to run it on the commit stage. Then you have processor in the loop at the acceptance test stage, hardware in the loop, and so on. And in the end, you want to run a system test or a hardware in the loop test, so reality system test or a hardware in the loop system test. The unit test can be used, usually a unit test framework, usually to run unit tests, software integration tests, and processor in the loop tests. And the mini-hill, for example, can support you with running hardware software integration tests, capacity tests, system tests up to a certain degree, and maybe also already an acceptance test for certain things. So let's have a look at the typical response time of the test levels. If you run a unit test, a component test, usually it takes a couple of minutes. So that's definitely something we want to run in the commit stage. A system test, even if it's a hardware in the loop system test, is very expensive, is very late in the process, so probably not run very often, and it's hard to automate. So that's why we usually have very slow response times here. Acceptance tests happen on the system tests level usually. That's why they take more or less like the same time like a system test. And with the mini-hill, so unit test tools here, and with the mini-hill, we can get the hardware software integration tests down to a couple of minutes, maybe an hour, something like this. So you get the fast response, even if you are already in the region, in the area of a system test. Not complete, but depending on the system, you can get pretty close to a system test. Here on the right side, you see such a test setup with an Oryx processor, automotive processor on the mini-hill board. I'll get into this a little bit later. So speed is the message. That's the whole point here. We want to fail fast. So let's keep it as simple as possible. Let's have a look at the mini-hill hardware platform we use to run this hardware software integration test. So on the right side, you see the system under test. That's in this case STM32 Cortex-M4 chip on an evaluation board, standard evaluation board by ST. You plug in your evaluation board here on the right side of the mini-hill. The blue area, that's the mini-hill. And on the left side here, you have a processor, Cortex-M7, a very fast Cortex-M processor to run the environment simulation and the test cases. Here in the middle, you connect the pins of the microcontroller you want to test, so the system under test, with your test system. For example, all the signals like PWM, digital, analog, SPI, and so on, all the low-level signals. And on the left side, now you need three things. You need your test system to connect somehow to those wires. So you need adapters for the IOs. Then you need environment simulations, because if you want to control a motor or a battery and you do not have attached a motor or a battery, then your system fails immediately. So you do not even get to the state where you actually can test the system, because it's not running. So you need to attach a real motor, or in our case here, to simulate a motor or a battery or a bus protocol, because then you can get the system into any state you want. And on top of that, you run your test cases and you can manipulate your simulation for failure injection and so on. So that's the hardware test setup. And now let's have a closer look inside this processor, how we develop this software to do the simulation and the test cases. For that, we have a development environment, a model-based environment, where you define the structure and the behavior for the environment simulations and the test models. From those models, we generate C code, we compile this, we flash it to the test system. Why don't we run it from a PC or another platform? Because we need it to be hard real-time. If you have a motor controller that runs with 20 or 30 kilohertz, you need the simulation to run with the 20 or 30 kilohertz. Or in a field-oriented control, this needs to be even faster. So you need hard real-time, and that's what you get with the mini-hill here. So also the test cases run with hard real-time down to 10 microseconds, 20 microseconds. So micro, not milliseconds. That's very important. Then we log the test results. We transform them into diagrams, because diagrams are much easier for human beings to read, and we want to interpret the problem as fast as possible. So that's why we do text logging, but we convert the text logs into fitting diagrams. And then we learn and we iterate. So a typical hardware in the loop setup on your desktop, that's what it looks like. You have the mini-hill, you have the laptop. That's exactly the setup I have here. So just to give you a glimpse, that's my setup here. And so that's typical setup for one project, maybe you push the button, you don't need continuous integration to do this, maybe. But if you have more developers, or the developers are distributed worldwide or in several locations, or the projects are just bigger, or you have more than one project, then probably continuous integration is a good idea. So every code change is automatically built and tested on the continuous integration server and probably delivered also. Here you see a test setup with 8 mini-hill boards. So for 8 different projects, every commit is tested also in hardware in the loop. That's the idea here. So that way you get every code change of every developer tested within minutes. So my continuous integration setup here on my desktop is, I have a laptop here, I have the mini-hill attached to it, I have the development environment of the mini-hill on my laptop, and I commit the tests to the Git source code management. This triggers the Jenkins continuous integration server, which builds and flashes and runs the tests on the mini-hill, and we generate the results. So that's the development of the tests, but this exactly the same process is automatically done if the system under test is committed, and that's essentially what I want to have. So whatever I change, a system under test or a test, it's always treated the same way. That also helps the test developer a lot. So the setup the test setup, the demo setup I'm going to show you now is a system under test with a Cortex M4 STM32 processor that runs a BLDC motor control. On the other side, I have the simulation, motor simulation. It measures the 3 PWMs, generates 3 Hall signals exactly as the real motor would do. It generates an analog signal for the temperature value the system under tests needs, and with the UART, I control the speed of the motor and start and stop it and so on, so things like that. Now let's dive into the demo. I'm going to show you what this looks like in the development environment. So here I have the demo component. Everything inside this box is generated, compiled, and flashed to the test system, because the system under test, that's your system. In this case, just a piece of C code that runs this BLDC motor controller. So, but basically that's already a normal test setup. We see at many customers. So in the model, on the lowest level, you have the I/O adapters, analog, digital, for example, UART, then the duty capture unit for the PWMs. They are measured, they are fed into the motor simulator. The motor simulator calculates the new speed and tells the whole generator with which frequency the 3 digital outputs should emulate a whole 3 Hall signals. So then on the next level, we have the simulation level. For example, a motor temperature simulator that just converts degrees Celsius into an analog output from 0 to 3.3 or 5 volt. And the motor simulator, this contains a motor simulation, can be a state machine directly generated from the state machine model here. So it directly transforms into C code. Very convenient way to create event-driven simulations. For a loopback controller, for example, for a plant simulation, you can also use a Simulink or Scilab simulation and generate C code from this and integrate this. So the last thing I want to show you is the test cases, because now we have the environment simulation. We can simulate the complete environment, and we can simulate the motor, the temperature, and so on. And now I want to break the system, basically. So I want to prove that it works by trying to break it. So fault injection and so on. So how I'm going to do this, I could create a state machine to do a test, but a state machine is not very efficient in creating a test. If you know it's a test, There are better ways to do this. For example, our language cage here, this integrates deeply with this test system here. So let's start with a step. For example, I want to request a new speed. I created a test step. The first action is I set a new speed, and then I check whether the system under test actually received the right speed and accepts the command. The next step I need is, for example, the check speed. That's a step I use to check whether the simulation, in this case, the simulation is working with the right speed, because the simulation is triggered by or is controlled by the motor controller. So the simulation knows the real speed of the system under test, and I use this to verify that the system under test works correctly. So if my speed is in a certain range, that's good. So here I can also break it by, for example, applying a wrong speed or a wrong signal and so on. So those are the low-level steps. We tend to make them reusable because on a level above, we want to create, just a second, we want to create test sequences. So sequences reuse test steps and sequences to create deeper tests. For example, here for certain requirements tests, we reuse those steps and the sequences. And in the end, we create a test suite that contains all the tests for this particular test setup. So that's the specification. So if I change anything here, you get automatically rendered the new specification. So that's very convenient, because that's the way how you develop the tests, and that's the way how you discuss the tests with your colleagues. So you always have the graphical specification automatically built. So that's how you build the tests and the simulation. So now let's, I can generate this now and flash this, and I can run this directly here from the graphical user interface. I'm connected now. So if I run this here and I break the system by pulling a plug here, so that's, now I see something does not work. I plug it in again, and now it's green again. So now I can, for example, click here on the problem, and then I get the highlighting here in the right step in my development environment, so that I know where my system failed. But that's not what we want. We want to test automatically. So let's have a look at what happens if I introduce a bug in my software. So for example, I create a problem here with my motor control system. So I set the duty cycle constantly to 20%, because that's something that should trigger some kind of problem. And now I'm going to commit this change. So now I'm on the system under test. I'm using the same development environment, but now I change the system under test and I introduced a bug. So just to demonstrate this, so now I check it in to my source code repository. It's a Git repository. Let's call this bug. I commit this, and after I've committed this, I immediately change to my continuous integration setup here. And here you see already that it just triggered the continuous integration server, and it's already running. So that's how fast it goes, because on every commit we trigger this. And now it's building, it's assembling, it's flashing. Here you see the lights have been flashing. So the system under test is flashed anew, the test system is flashed new, and now the tests are automatically being run on the test system, on the mini-hill board, and we can have a look at what happens here. That's a text logging. It's just interesting if you need more details. What's really interesting is the reporting here. So you see it's yellow. So that means the tests, some tests failed. It could build, but some tests failed. So we have 3 tests that failed. For example, the demo integration test, limit temperature, motor control speed, and so on. So let's go back and have a look at what really happened, because I also get the traces I've shown you before in the same format here in the continuous integration server. And here I see which test failed on the server. So server, of course, is running locally on my machine here, but it could also be on any server you run. So expect failed, I click on that. And here I get the exact place where my test case failed. And now it's up to you to fix the bug. So now I can fix the bug and commit it and immediately run the test again. I don't even have to wait for it. I can continue my work because I will get an email if the test is okay again or if a test failed. So that's it so far. I hope you enjoyed the presentation. If you have any questions, please don't hesitate to contact me. You will find my contact information here on the last slide. We will send you afterwards an email with the recording of this webinar. So please don't hesitate to contact me if you have any further questions. Thanks for your attention. It's been a pleasure, and have a nice evening. Bye-bye.